Welcome to this explainer. Today, we're diving into a topic that is quite literally redefining the limits of human capability, and that is the rapid growth of supercomputers. It's a space that moves so incredibly fast, rewriting the boundaries of computational science year after year, and it is absolutely fascinating to watch. Take a look at this number, 2.198 exaflops per second. Yeah, let that sink in for a second. That staggering figure represents the sheer, record-breaking speed of the new #1 supercomputer in the world, at least according to the June 2026 TOP 500 list. But to really appreciate what a massive number that is, we need just a little bit of context. To grasp what we're actually dealing with here, we have to define the exascale era. An exascale computing system is capable of calculating at least 1 quintillion floating point operations, or basic math equations, every single second. That's a 1 followed by 18 zeros every single second. It's a monumental milestone in hardware engineering that finally lets us process the universe's most complex data. So here is our roadmap for today. We'll start with the exascale computing era. Look at who is leading the top 500 list, and then see how these machines are decoding the universe's particles, simulating nuclear fusion energy, and finally, we'll look ahead to the quantum horizon. All right, let's jump into part 1, the exascale computing era. Looking at the June 2026 TOP 500 list, we officially have 5 unique exascale class systems operating globally. And that's huge, because we aren't just talking about one lone experimental machine anymore. We have an entire class of machines actively pushing the boundaries of what is computationally possible all across the globe. Moving right along to Section 2, leading the top 500 list. The international landscape here is fiercely competitive right now. China's Lineshine holds the crown, but the US is right on its heels with 3 absolute behemoths: El Capitan, Frontier, and Aurora. Rounding out the top 5, we have Europe's very first exascale system, the Jupiter Booster, over in Germany. It's wild to see how these RMAX performance numbers and the massive core counts driving them are just steadily climbing across the board. Let's zoom in on that new champion for a second. Debuting at #1 out of Shenzhen Lineshine, achieved its massive lead using an unbelievable 13.7 million cores. What's truly fascinating here is that it's built on a custom Lincoln platform using CPU-only design. Hitting 2.198 exaflops, it basically crushed the benchmark, sitting more than 20% ahead of the second-place system. And just behind it is El Capitan at the Lawrence Livermore National Lab. It's packing over 11.3 million cores and hitting 1.809 exaflops. But honestly, El Capitan's real superpower is its energy efficiency. It is squeezing out nearly 61 gigaflops per watt using AMD processors, which is just an incredible feat of engineering. Which brings us to Section 3, decoding the universe's particles. Now, let's look at how this power actually gets used, because there's a really fascinating architectural contrast out there. Unlike those massive unified machines sitting in a single data center like Lineshine, the Large Hadron Collider uses something called a grid. This grid literally links regular desktop computers across 170 locations in 36 different countries, networking them into one colossal decentralized supercomputer. This decentralized approach is literally the only way scientists can sift through the insane amount of data generated when high-energy particles smash together. The grid takes all that highly sensitive detector data and processes it, which is exactly how researchers were able to study these interactions and spot predicted standard model particles, like the famous Higgs boson. All right, Section 4, simulating nuclear fusion energy. It's not just particle physics either. Over at the ITER project, supercomputers are running complex simulations of energetic particles hitting temperatures of roughly 15 billion degrees Celsius. Scientists need this immense computing power to model phenomena like the fishbone instability. They basically need to see exactly how these particles behave in the core plasma and figure out if they'll cause disruptions to the fusion reaction. And here is where it gets really cool. Thanks to these advanced simulations, an international team made a huge breakthrough. They found out that these extreme energetic particle-driven instabilities aren't always a bad thing. Actually, they can self-generate strong flows within the plasma that help heat it up, which increases the overall fusion performance. It's a totally counterintuitive finding, and it was made possible entirely by high-performance supercomputing. Plus, They're using supercomputers to model the physical hardware of the reactor itself, using the new Memento melt code. ITER recently decided to switch its first wall armor material to solid tungsten. So, researchers are actively simulating how a burning plasma might interact with and potentially melt those tungsten walls during power spikes. It's predictive modeling that directly shapes how we build reactor-scale devices. Finally, Section 5, the quantum horizon. Now, brace yourself for this one. Even with the LHC's massive global grid supercomputer, as vast and powerful as it is, they are currently only able to process about 1% of the data coming from the detectors. 1%. 99% of that data just goes unprocessed, because even our absolute best distributed networks can't handle the sheer volume. Since we are leaving so much data on the table, we're essentially hitting a physical brick wall with classical computing architecture. And that limitation? It's the primary driver motivating the massive push toward quantum computing. Scientists are hoping to take the very quantum mechanics lessons learned at the LHC and use them to build entirely new, exponentially faster types of computers. So I want to leave you with this to ponder. As our scientific ambitions outgrow even a 13 million core supercomputer, is the quantum horizon the only viable path forward for human discovery? The rapid growth of supercomputers has definitely brought us to the edge of the known universe. But to cross that final frontier and unlock that missing 99% of data, we might need a fundamental shift in how we compute. Thanks for joining me on this explainer, and definitely keep your eyes on that horizon.